It's a different universe, James Webb found. Another problem. Something extraordinary is happening right now at the frontier of human knowledge. A telescope, drifting through the cold silence of space, is peering back across 13 billion years of cosmic history, and what it keeps finding refuses to match anything scientists expected. Galaxies far too large for how young they are. Black holes that grew to enormous sizes before physics says they had time to do so. Chemical elements that shouldn't exist yet, scattered through galaxies that had barely begun to form. A universe that was supposed to begin as something quiet and primitive, but turned out to be loud, organized, and shockingly advanced. Every time astronomers find a way to account for one contradiction, the next image from the James Webb Space Telescope delivers another. This is what Webb has been revealing, and why many researchers now suspect that the universe may be fundamentally different from what we thought we understood. The first image and what it said. On July 11, 2022, a small team of scientists gathered around a monitor at the Space Telescope Science Institute in Baltimore. They had spent years preparing for this moment. The first deep-field image from James Webb was about to appear on that screen. When it did, the room went silent. The image covered a patch of sky so small that you could hide it behind a grain of sand held at arm's length. Inside that tiny sliver of darkness were thousands of galaxies. Some were relatively close, glowing in familiar shapes. Others were so remote that their light had been traveling through expanding space for most of the universe's existence. Their colors shifted deep into the infrared by billions of years of cosmic stretching. But the real story wasn't in the beauty of the image. It was in the numbers that came back when astronomers began carefully measuring the most distant objects within it. Those ancient, remote galaxies were wrong. According to every model of how the cosmos develops, galaxies seen at that distance, existing when the universe was only a few 100 million years old, should look primitive. Faint, irregular, barely assembled collections of young stars with modest mass and little structure. The standard picture of early cosmic history is one of gradual, patient construction, a universe slowly building itself from the simplest possible beginnings. What Webb showed instead was something far more difficult to explain. Many of these ancient objects looked complete, organized, massive. They resembled fully developed galaxies. The kind of thing that should take billions of years to assemble, sitting in an era when the universe had barely gotten started. One scientist later described the feeling as looking at a baby photograph and seeing a fully grown adult staring back. Senior researchers called it a quiet panic. Models refined over 4 decades suddenly looked wrong. Teams stayed up through the night running simulations, trying to reproduce what Webb had captured. The simulations failed, and this wasn't an isolated anomaly from a single team or one unusual corner of the sky. The signal appeared everywhere Webb pointed. Not 1 or 2 impossibly developed early galaxies, but dozens, then hundreds, each one more mature than it had any right to be for its age. Some showed clear internal structure. Some contained heavy chemical elements like iron and oxygen, which require multiple generations of stellar birth and death to produce. Some appeared to already host central supermassive black holes actively consuming surrounding gas. This was not a minor adjustment to an otherwise intact framework. It was a crack running through the foundation. How galaxies are supposed to form. To appreciate why these findings struck so hard, it helps to understand how a galaxy is supposed to come into existence. According to the standard model, the process begins with dark matter clumping together under gravity, forming an invisible cosmic skeleton. Ordinary matter, mostly hydrogen and helium, fell into those gravitational wells, compressed, cooled, and eventually ignited as stars. Those stars lived, died as supernovae, and scattered heavier elements back into surrounding gas. New stellar generations formed from that enriched mixture, and the cycle repeated. Galaxies slowly accumulated mass, structure, and chemical complexity across billions of years. The Standard Model is, at its core, a story about gradual assembly. The early universe should have been full of half-finished structures, small, irregular, immature collections of young stars, just beginning the long process of becoming something recognizable as a galaxy. Webb kept finding completed cities, the universe breakers. In early 2023, a team led by astronomer Ivo Labbé published a paper that quietly detonated inside the field. They had analyzed Webb data and identified 6 galaxies that the Standard Model simply could not account for. The team gave them an unofficial name that spread quickly through the astrophysics community: the universe breakers. The reason was straightforward and brutal. These 6 galaxies existed when the universe was only 500 to 700 million years old. According to standard physics, the most massive galaxies from that period should contain the equivalent of a few billion solar masses at most. The universe breakers contained tens of billions. Some estimates pushed certain objects past 100 billion solar masses, roughly equivalent to the entire stellar mass of the Milky Way today, crammed into an era when the universe shouldn't have had the raw material to build anything remotely like it. To produce that much stellar mass in such a compressed window, gas would have needed to convert into stars with almost perfect efficiency. Nearly no waste, nearly no material blown away by radiation or thermal pressure. Real galaxies don't work that way. Star formation is slow, messy, and inefficient under normal conditions. The early universe, more chaotic by every expectation, should have been even less efficient, not more. Critics attempted alternative explanations. Could these objects be supermassive black holes shining so brightly they mimicked entire galaxies? Could 2 distant galaxies be overlapping on the sky? Could there be errors in their distance calculations? Each possibility was tested and scrutinized. While a handful of the original 6 showed unusual properties that softened the problem somewhat, several remained stubbornly resistant to any clean explanation. One in particular became well known across the field. It appeared to contain roughly the same number of stars as the Milky Way. Yet it existed when the universe was only about 5% of its current age. There is no clean explanation for that within current physics. The name universe breakers stuck because the implications genuinely threaten the theoretical framework cosmology has been built on. If even one of these galaxies is real, and if its mass estimate is accurate, then the early universe must have operated under rules that haven't been discovered yet. Some researchers proposed that dark matter scaffolding could have assembled faster and more densely than any simulation predicted. Giving galaxies a gravitational head start the standard timeline doesn't allow. Others suggested the early cosmos may have undergone brief moments of unusually intense gravitational collapse, cosmic pressure points where matter clumped in ways modern equations can't describe. A few proposed that the very first stars were monsters, hundreds of times more massive than the Sun, collapsing into black holes almost immediately and pulling in surrounding material at speeds the standard timeline never allowed for. None of these ideas have been confirmed, but the fact that they are being seriously discussed inside mainstream science tells you something important about the state of the field. The universe breakers are not curiosities at the edge of the data. They are warnings, spiral galaxies where none should exist. If the universe breakers shook cosmology by revealing galaxies too massive for their age, the next discovery rattled something equally foundational. Not just how large early galaxies were, but what they looked like. And what they looked like was something they had absolutely no business looking like at that stage of cosmic history. Spiral galaxies are among the most visually striking structures in existence. The Milky Way is one. The Andromeda Galaxy is another. They feature flat, rotating disks, sweeping arms that curl gracefully outward from a bright central bulge, and a highly organized rotational motion that makes them look almost architectural from a distance. When you encounter one in an image, it reads immediately as something mature and settled, the product of a long process that took billions of years to complete. For decades, that was exactly how astronomers understood them. The textbook story placed the formation of true spiral galaxies at roughly 6 to 8 billion years after the Big Bang. Before that threshold, the universe was supposed to be fundamentally different: violent, turbulent, full of frequent collisions. Galaxies from that era were expected to appear lumpy and irregular, like rough sketches rather than finished structures. The organized beauty of a spiral disk was supposed to require billions of years of settling, cooling, and gravitational refinement. Webb dismantled that assumption almost immediately. When the telescope examined deep-field galaxies, it found objects with unmistakable spiral structure dating back to just 1 to 2 billion years after the Big Bang. Not faint suggestions of disks, not blobs with a subtle rotational lean. Full, organized multi-armed spirals with bright central bulges, clean rotation patterns, and structural detail matching galaxies we observe in the modern universe. They looked, in the words of one astrophysicist on the team, like finding a fully built city in what was supposed to be an empty wilderness. To understand why this is such a problem, consider what a spiral disk actually requires. Gas arriving in a young galaxy is hot and chaotic. Random clouds collide at high velocities. Violent bursts of star formation send shock waves tearing through surrounding material. For a stable disk to form, that chaos has to calm down significantly. The gas has to cool. Stars have to settle into coherent rotating orbits, and spiral arms require a smoothly rotating disk through which gravitational density waves can propagate in long, self-sustaining patterns. That requires a system that has already found its equilibrium, a process thought to take many cosmic generations. Webb's data showed galaxies achieving it in a fraction of the expected time. A research team analyzed a large sample of early galaxies, expecting disk shapes to represent perhaps 10% of what they found. The actual result came back above 50%. More than half of galaxies in their early universe sample showed clear disk structure. A spiral disk is not just a shape. It is evidence of order, of a system that has had time to find its equilibrium and settle into sustained organized motion. These are the hallmarks of maturity. And maturity, in the cosmic sense, is supposed to require time that the early universe simply had not yet accumulated. Webb is showing us a universe that was mature before it had any right to be. Black holes that arrived too early. There is a relationship in astrophysics that has held remarkably well for decades. The bigger the galaxy, the bigger the black hole at its center, with a consistency so reliable that astronomers treat it almost as a law of nature. A typical supermassive black hole weighs about 1/10% of its host galaxy's total stellar mass. The correlation is tight, predictable, and confirmed across thousands of galaxies in the modern universe. Webb has found something in the early universe that breaks it completely. When the telescope examined ancient galaxies from the universe's first billion years, the black holes at their centers were wrong. Not slightly oversized. In some cases, the black hole appeared to outweigh the entire stellar content of the galaxy surrounding it. The monster at the center was larger than the city it was supposed to be living inside. This inverts the story we thought we understood. The standard model assumes galaxies come first. Gas collapses, stars form, a galaxy takes shape, and the central black hole grows alongside it, fed gradually by infalling material over billions of years. What Webb is suggesting instead is a picture where the black hole arrived first, where it formed, swelled to extraordinary size, and then pulled surrounding gas in to construct a galaxy around it afterward. Almost like a monument erected before cities that would eventually surround it. But the problem runs even deeper, into a hard wall of fundamental physics. Black holes cannot feed at unlimited speeds. As matter falls inward, it heats up and radiates energy outward. That radiation pushes against the infalling material, slowing accretion. At a threshold called the Eddington limit, outward radiation pressure exactly balances inward gravitational pull, and accretion effectively stalls. The Eddington limit is not a soft guideline. It is a physical ceiling, and it applies universally. Even starting from a generous initial mass and feeding continuously at the Eddington limit without pause, growing a black hole to 1 billion solar masses takes longer than the early universe had been in existence. The math simply doesn't close. Yet Webb has confirmed billion solar mass black holes at the centers of galaxies that existed less than 700 million years after the Big Bang, in some cases even earlier. Astronomers have proposed several exits from this contradiction. The first is direct collapse black holes, enormous gas clouds in the early universe that never fragmented into stars, instead collapsing directly into a single massive object. A black hole born weighing millions of solar masses from the very beginning, with no intermediate stellar stage. A head start of that magnitude changes the growth calculation entirely. The difficulty is that direct collapse has never been directly observed and remains a hypothesis without confirmation. A second theory suggests that early black holes may have temporarily exceeded the Eddington limit under the extreme conditions of the young universe. Some simulations support this under very specific conditions, but sustaining those conditions long enough to explain what Webb is finding strains even generous physical assumptions. A third possibility reaches back to the first moments after the Big Bang. Primordial black holes, objects formed in the violent instants immediately following the Big Bang, before any stars or galaxies existed, could have provided pre-made seeds of enormous mass. The idea has circulated in theoretical physics for decades. Webb's findings are giving it a serious second look. Webb has also been detecting a peculiar class of objects at the extreme end of this phenomenon. Tiny, intensely red points of light scattered across the deep field images, so compact they were initially dismissed as noise. Closer analysis revealed that many of these objects, now informally called little red dots, appear to host supermassive black holes so massive relative to their surroundings that the black hole accounts for nearly the entire detectable mass of the system. They are almost pure black hole, with just enough surrounding material to register as a galaxy at all. Webb has found hundreds of them. They were not rare anomalies. They were common. Chemistry that arrived too early. Every atom, heavier than helium, was forged inside a star. That statement is one of the most foundational principles in modern astrophysics. Hydrogen and helium emerged from the Big Bang itself. Everything else, the iron in your blood, the oxygen in every breath, the carbon backbone of every biological molecule, none of it existed at the beginning. It had to be built inside stars. A massive star spends millions of years fusing lighter elements into progressively heavier ones. When it exhausts its fuel, it explodes as a supernova, scattering those elements across surrounding space. New generations form from that enriched material, building further on what came before. Repeat across hundreds of millions of years, and the universe gradually accumulates the chemical complexity we observe today. The operative word is gradually. Standard models place the threshold for significant chemical enrichment at a minimum of 1 to 2 billion years after the Big Bang. Webb found iron and oxygen in galaxies that existed less than 500 million years after the Big Bang, in some cases at concentrations approaching those found in modern galaxies. A research team checked their measurements multiple times before publishing. The data held every time. The leading candidate for explaining this is the first generation of stars, a hypothetical population known as Population 3 stars. These would have been the universe's very first stellar objects, forming from pure hydrogen and helium with no heavier elements. Without metals to help gas cool and fragment, these clouds couldn't break into small pieces. Theory predicts they would have been enormous, hundreds of times more massive than the Sun, burning at extreme temperatures, living only a few million years. then exploding as extraordinarily powerful supernovae, seeding their surroundings with the first heavy elements in existence. Their explosions would have been powerful enough to distribute heavy elements across vast volumes of gas quickly, and the early universe was smaller and denser than today, allowing that material to mix through galaxies far more rapidly. The argument is plausible on the surface, but here is where the mystery folds back on itself. Webb has been searching for direct evidence of population 3 stars since the telescope first opened its mirror. These objects should produce clear signatures. The gas they ionize should glow in specific characteristic patterns. Their explosions should leave distinct chemical fingerprints. Their light, red-shifted across billions of years, should fall precisely within the infrared wavelengths Webb was specifically designed to detect. This is the most sensitive instrument ever pointed at the early universe. If population 3 stars exist in the numbers and with the properties that models predict, Webb should be finding them. The signals are not appearing, or when they do appear, they are far weaker and far rarer than expected. This creates a deeply uncomfortable situation. The chemical enrichment is real, confirmed through multiple independent measurements. The heavy elements in those early galaxies are not a data artifact, but the source that theory depends on to explain that enrichment is not showing up in the data. It is as though a fire burned through a forest, leaving unmistakable char and ash everywhere, but no trace of any flame. Several explanations are being considered. One is that population 3 stars existed, but were smaller and less luminous than models predict, burning cooler and living longer, leaving fewer dramatic traces and blending into the background of later stellar populations. Another is that they formed in brief, isolated pockets of the early universe, in numbers too small and over timescales too short to leave a strong, detectable signal across cosmic distances. A third possibility is more unsettling. Perhaps population 3 stars simply did not behave the way theory predicts at all. Perhaps the conditions of the early universe produced a first stellar generation that looked fundamentally unlike what decades of modeling have been expecting. If their properties were substantially different from the massive, hot giants that theory describes, then every model built on the assumption of their standard properties would need to be rebuilt from a different starting point. Population 3 stars are not a minor detail in the cosmic narrative. They represent the chapter that connects the featureless simplicity of the Big Bang to the chemical richness of everything that followed. Their existence and properties are woven into nearly every model of how galaxies evolved, how planetary systems formed, and how the raw ingredients for life came to be distributed through the cosmos. If Webb continues to fail to detect them in the form that theory predicts, that chapter may need to be rewritten entirely. The broken rule. There is a number at the heart of modern cosmology, a single value that determines the age of the universe, the size of the observable cosmos, and the ultimate fate of everything that exists. It is called the Hubble constant, and it measures how fast the universe is currently expanding, how quickly galaxies are moving apart from one another as space itself stretches in every direction. Get this number right, and the entire timeline of cosmic history follows. Get it wrong, and everything built on top of it shifts. For decades, two independent methods of measuring the Hubble constant kept returning answers that were close, but not quite the same. As instruments improved and measurements became more precise, most astronomers assumed the gap would eventually close. Instead, as precision increased, the gap widened. The first method looks backward in time. Satellites like the Planck Observatory mapped the cosmic microwave background, the faint afterglow of radiation from the early universe, with extraordinary precision. By analyzing temperature patterns in that ancient light, physicists calculate the universe's current expansion rate. The answer, approximately 67 kilometers per second per megaparsec. The second method looks at the universe today. Astronomers measure objects of known intrinsic brightness, standard candles, to calculate distances, then map those distances against how fast galaxies are receding. The most commonly used standard candles are Cepheid variable stars and Type Ia supernovae. The answer: approximately 73 kilometers per second per megaparsec. 67 versus 73. The difference sounds modest. In cosmology, it is a chasm. The universe cannot be expanding at two different rates simultaneously. Both measurements are precise. Both have been tested, refined, and confirmed by multiple independent teams using different instruments and techniques. Neither is going away. The disagreement between them, now called the Hubble tension, has become one of the most stubborn and consequential unsolved problems in modern science. When Webb launched, many researchers hoped the telescope would cut through the tension. Its extraordinary infrared sensitivity made it the ideal instrument for observing Cepheid variable stars in distant galaxies with a level of clarity no previous telescope could achieve. The hope was that Webb would reveal a subtle systematic error buried in one of the measurements, and that correcting it would bring the two values into agreement. Webb delivered cleaner measurements than anyone had previously achieved. The tension remained. Not only did the locally measured expansion rate hold firm near 73, but Webb's sharper observations introduced new complexity. Some Cepheid stars, examined with Webb's precision, appear to behave slightly differently in distant galaxies than in nearby ones. The pulsation properties that define their usefulness as standard candles showed subtle variations that previous telescopes lacked the resolution to detect. These variations are small, but in a field where the entire argument hinges on a 6-unit difference, small variations in the fundamental measuring tool carry serious weight. Type Ia supernovae also came under renewed scrutiny. Their peak brightness has been assumed consistent enough across the universe to serve as a dependable cosmic ruler. Webb's observations began revealing that this consistency may have limits. The chemical composition of a host galaxy, its age, and its star formation history appear to leave subtle imprints on the supernovae it produces. If the ruler is even slightly miscalibrated, the consequences ripple outward through every measurement built on top of it. This connects directly to every other anomaly Webb has uncovered. Galaxies that appear too massive might simply be at slightly different distances than calculated. Black holes that seem to have grown impossibly fast might have had more time than the current timeline allows. Chemistry that arrived too early might fit more naturally into a slightly extended cosmic history. This is why the Hubble tension is not just a technical disagreement between two groups of astronomers. It is a load-bearing crack in the foundation. If the expansion rate is wrong, the age is wrong. If the age is wrong, the timeline is wrong. And if the timeline is wrong, then many of Webb's most troubling discoveries may not be violations of physics at all. They may simply be evidence that we have been working with the wrong clock. What it all means. Step back for a moment and look at the full picture of what Webb has returned. Galaxies too massive for their age, assembled at speeds the standard model has no mechanism to accommodate. Black holes too large for their host galaxies, arriving far too early for the physics of accretion to explain. Spiral disks forming with organized maturity that the violent early universe was never supposed to permit. Heavy chemical elements appearing hundreds of millions of years ahead of schedule, apparently produced by a first stellar generation that the telescope cannot find in the form theory predicts. A persistent, widening disagreement between two independent measurements of the universe's expansion rate, sitting at the center of modern cosmology like a fault line that refuses to close. Each of these discoveries, encountered in isolation, might be absorbed into the existing framework with careful adjustments and patient recalibration. Encountered together, they form something considerably harder to dismiss. They form a pattern. The standard cosmological model is not collapsing. It still explains the large-scale structure of the universe with impressive accuracy. It still correctly accounts for the cosmic microwave background. It still successfully predicts the primordial abundances of hydrogen and helium. These are genuine achievements, and nothing Webb has found erases them. But the model has edges, places where its predictions meet the observational data, and the fit is no longer clean, and Webb keeps finding those edges in every direction it looks. Something is incomplete. The most conservative possibility is that the universe is simply somewhat older than our current estimate of 13.8 billion years. Even a modest extension of the timeline, pushing the age to 14 or perhaps 5 billion years, would dissolve many of Webb's most troubling findings without requiring any change to fundamental physics. Galaxies would have more time to assemble. Black holes would have more time to grow. Heavy elements would have more time to accumulate across multiple stellar generations. A miscalibrated cosmic clock, running slightly fast, could quietly resolve more of Webb's contradictions than any other single adjustment to the model. The second possibility is that dark matter does not behave the way the standard model assumes. Cold dark matter, slow-moving, smoothly distributed, clumping hierarchically from small structures to large, has been the backbone of cosmological simulation for decades. But Webb's galaxy clustering data, its rotation measurements, and the sheer pace of early structure formation are beginning to favor something more complex. Warm dark matter, fuzzy dark matter, self-interacting dark matter. Each of these alternatives fits different aspects of Webb's observations more naturally. The field is beginning to take them more seriously than it has in years. The third possibility cuts deeper. Gravity itself, the force that governs everything from a moon's orbit to the large-scale architecture of the cosmos, may not behave identically across all scales and all epochs. Modified gravity theories have circled the edges of mainstream cosmology for decades. Webb is giving them a new hearing. The rotation patterns of early galaxies, the clustering of large-scale structure, the behavior of galaxy clusters, all carry signatures that standard gravity combined with standard dark matter struggles to cleanly reproduce. If gravity has a scale dependence that current equations don't capture, the implications would extend through every calculation in cosmology. It would not be a small revision. It would be a foundational one. The fourth possibility is the most radical. The early universe may have operated under physical conditions so extreme and so unlike anything that exists today that the structures it produced cannot be reproduced by equations calibrated on the modern cosmos. Perhaps the first few 100 million years represent a regime of physics that current theories were never designed to describe. A universe temporarily governed by a different set of effective rules, before settling into the calmer behavior we observe today. This idea is speculative, with no confirmed theoretical framework behind it. But the consistency with which Webb keeps finding the early universe outside the bounds of current models is pushing some researchers in exactly this direction. The history of physics offers useful perspective. In the early 20th century, the discovery that light and matter behaved in ways classical mechanics could not explain didn't add a correction term to existing equations. It revealed quantum mechanics, an entirely new layer of physical reality that classical physics had no language for. Something similar happened when observations of distant supernovae in the late 1990s revealed that the universe's expansion was accelerating. The existing model had no room for it. The response was to introduce dark energy, an entirely new component of reality, and rebuild the standard model around it. Webb may be generating the observations that precede the next such moment. Not a correction, not a refinement, a revelation that the model describing the universe is missing something real. Something that will seem obvious in retrospect, the way quantum mechanics and dark energy seem obvious now. The anomalies Webb is accumulating are not scattered and unrelated. They cluster around the same cosmic era and point toward the same conclusion. The early universe was faster, more structured, more chemically advanced, and more extreme in almost every measurable way than the Standard Model predicted. Whatever drove that behavior left fingerprints across the entire subsequent history of the cosmos. Fingerprints that are becoming harder to ignore with every image the telescope returns. We are at the beginning of this reckoning. The data continues to accumulate. New telescopes are being planned. New theoretical frameworks are being constructed. The universe is not finished surprising us. What Webb has given us is not a crisis to be managed. It is an invitation to look more carefully, think more broadly, and hold our assumptions more lightly than we have been accustomed to. The cosmos is under no obligation to fit the models we built for it, and the picture coming back from 13 billion light-years away suggests, with growing clarity, that it never did.